So as we said, convection involves fluid motion as well as heat conduction, as is shown in this example. Now, heat transfer through a solid is always by conduction, while heat transfer through a fluid is by convection in the presence of bulk fluid motion and by conduction in absence of it. So if you have quiescent fluid that is not moving, you can have heat transfer through this fluid by conduction. But as we said, conduction is fluid is very poor, okay? It's small because you have particles that are very far from each other. So this is why, in general, when you have forced convection, you force your air to move, and this will induce convection between the surface and the flow. Okay, so another process where you have convection is called natural convection. In natural convection, you don't need to blow air over the surface. By just having air over the surface, once air is heated at the proximity of the hot surface, okay, it will gain kinetic energy. And due to this kinetic energy, it can move upward, okay? And in this case, you are transferring heat from conduction in the solid to convection in your flow. So when you don't force air to move, and it's moving only due to difference in density, this is called natural convection. Therefore, conduction in a fluid can be viewed as the limiting case of convection, corresponding to the case of quiescent fluid. And the rate of heat transfer through a fluid is much higher by convection than by conduction, as we have already seen. In fact, higher is the velocity of fluid, higher will be the rate of heat transfer. This is why, in general, heat transfer by forced convection is higher than heat transfer by natural convection, because you are increasing the kinetic energy of air, and air motion will induce heat transfer by convection. And how to calculate this? How to calculate convective heat transfer? The formula for convective heat transfer is given by the following. It is equal to, so convective heat transfer Q. So Q convection is calculated as H times A times delta temperature. Okay? And here, yes? Yes.
It was something just as long as the regions is another region.
Sorry, I cannot hear you well.
Basically a summary of history.
Can you please write in chatting? Because I cannot hear you here. Can you write what you want in chatting, please? Okay, so let us continue. So Q convection is calculated by H times A times delta T, where H is the convection coefficient. So if you do a comparison, in conduction you have the conduction coefficient K, and in convection you have the convective coefficient H, okay? And H also is calculated by experiments. So, and H depends on a lot of factors, as we will see. It will depend on the fluid properties, it will depend on the velocity of the fluid medium, and many other effects that we will talk about in next slides. Okay, so Q convection is H times the area of contact. So here, if you have contact between solid and the fluid, it's the area of contact between the two. And delta T is the variation in temperature within your flow. Okay, so we will go in detail over this equation in the next slides. Okay. Now, convective heat transfer depends on a lot of factors, including the fluid properties as dynamic viscosity, thermal conductivity, density, specific heat, as well as the fluid velocity. In addition, it also depends on the geometry and the roughness of the solid surface, in addition to the type of the fluid flow. So if it's a turbulent or laminar flow, it will be different, okay? This is why calculation of convection coefficient is very complex, okay? Because it depends on a lot of factors. And what we do is we perform experiments to come up with empirical relations that can work in general cases, okay? So always H, you need to get it from tables or from empirical developed relations in experiments. Now, the heat flux per unit area of convection is defined as the convective coefficient A times delta T, where delta T is the difference between the surface temperature and the ambient fluid temperature. So T infinity is the temperature of the fluid that is far from the surface, okay? And Ts is the surface temperature. So for example, if you have a solid surface and you blow air over the surface, let's say I give you that the temperature of the surface is 50 degrees, as in the previous example, and we are blowing air over it with its initial temperature of 20 degrees. So you can say that very far from the surface, the temperature will be the temperature of the fluid, which is 20 degrees. This is called T infinity, okay? So this is T infinity, which is the temperature very far from the surface. And Ts is the surface temperature, which is 50 degrees. So in this example, you replace Ts by 50 and T infinity by 20. Now, if you want to find the rate of convection in watts, you should multiply small q dot convection by the surface area. The surface area, for example, here, if you have a plate, if your surface is in the form of a plate, okay, then the surface area you consider is this one, which is the area over which air is going over, okay? So it's H times A surface, which is here the area of this rectangle, times Ts minus T infinity. Now how to predict this term, H, okay? In order to find H, we need to know the type of the flow, okay? So first, it's a flow over a flat surface. So you can go to a certain appendix where you have relations for flow over flat surface. You need to know information about your fluid. So what is your fluid? It is water, it is air, okay? In order to know what is its viscosity, what is its conductivity, etc., density, and we will see an example how we do this, okay? Then you need to know if your flow is, let's say, turbulent or laminar. Do you know how we determine if a flow is laminar or turbulent? First, do you know what is a laminar flow or turbulent flow?
Reynolds number?
Yes, very good. So look, if you have a flow, if you look at a flow, okay, and you can see clear streamlines that are smooth, so you have a flow that is called laminar flow, okay? It is very ordered, it's moving along streamlines that are parallel to each other. This is called laminar streamlined flow. On the other hand, if you increase a lot, for example, the velocity, more you increase your velocity, more you will have disorder in your flow. And you will start to have circulation in your flow, okay? So you will start to see some curls in your flow, and it is disordered, it's not moving anymore along parallel lines, okay? This is called a turbulent flow. Now, how we define in fluids the difference between laminar and turbulent flow? we calculate a parameter called Reynolds number that we will introduce in the next slide. From the Reynolds number value, you can know if your flow is laminar or turbulent. And based on this, you will decide which empirical formula to use for H, because H will vary if it's a turbulent flow, okay? And we will see in examples how we can calculate H. Now, in order to understand more what is happening when you have a flow going over a flat plate, okay, you need to know some concepts in fluids. First, you need to know what is the no-slip condition, okay? When we say no-slip conditions, this means that whenever your fluid is in contact with a surface, then the fluid will take the same velocity of the surface. So for example here, in this example, you have a fixed plate, okay? This plate is fixed. Because it's fixed, the velocity of the plate is 0. So here V plate is equal to 0. And due to the no-slip condition, then the velocity of your fluid when it comes into contact with the plate should be also 0. So you are forcing your flow to start by a velocity of 0 at the plate level, okay? While your fluid is initially at a velocity, a uniform velocity, big V. So now the velocity inside your fluid will not be constant because you imposed a velocity of 0 at the plate level, and you have a velocity very far from the plate equal to V. So you will have a transition zone, okay? You will have a transition zone where the velocity will vary from 0 to big V. This is why we say that we have what we call the development of a boundary layer profile, okay? And to understand this, you can look here, for example, at this figure. You can see how close to the surface, okay, you will have gradient and velocities. This is why, if I want to draw it here, this is your boundary layer. It will look like this. So, okay, because outside of your boundary, you have uniform velocity. So everywhere outside of the boundary layer, you have uniform velocity equal to big V, okay? While inside your boundary, you have variation of velocity from 0. So velocity is starting by 0, and then it's increasing until reaching V. So at each level of your plate, you will have a small zone, which is a transient region, where the velocity is varying from 0 to V, okay? And this will lead to the development of what we call the boundary layer, which is of this form, okay? Now, we go back to the calculation of the convective coefficient, okay? So, due to the no-slip condition, okay, we have an implication that heat transfer from the solid surface to the fluid layer adjacent to the surface is by pure conduction. Why we say this? Because due to the no-slip condition, at the level of the surface, the fluid particles in contact with the surface will have a velocity of 0. So you will have a small layer of fluid that is motionless. It's not moving. And we said that when we have a layer of fluid that it's not moving, heat is transferred in this layer by conduction, okay? This is why we say that at the first level, at the contact between the surface and the fluid, we have a heat flux by conduction. And then when we go far from the layer in contact with the surface, which we will have motion of the fluid, then heat is transferred by convection. And due to conservation of energy, since we are working in steady state condition, the heat flux by conduction will be equal to the heat flux by convection. So we can say that Q dot convection in the fluid is equal to Q dot conduction in the fluid. And how to calculate Q dot conduction? It's simply minus K of the fluid, which is the conductivity of the fluid, times del T by del Y at Y equals to 0. And we mean here by Y equal to 0, so this is at the surface level. So this is at the surface level. Okay? So now, from this equation, you will find a relation between the convective coefficient A and the conductivity of your fluid. Okay? Because we know that we can replace Q convection by what? We go back to this equation. Okay? This is the conductive term. It is equal to the convective term. Okay? So this is equal to the convective flux, which is H times, because here we are calculating per meter square the flux, it's watt per meter square. So we just multiply H by delta T, which is T surface minus T infinity. Okay? And in general, you can express both rates in watt. So if you express in watt, all you have to do, you multiply here by the area. Okay? And here also you will multiply by the same area, because the cross-sectional area of conduction is the same as the area of contact between the fluid and the surface. So A will be simplified. You can simplify A, and then you express your flux in watt per meter square. And due to this equality, you can compute what is H. So H is simply minus K of the fluid times del T by del Y at the surface over Ts minus T infinity. But as you can see from this expression, in order to compute H, you need to know what is the gradient of temperature at the surface. And this can be measured in experiments. This is why you need experiments to find convective coefficients. Now, the convection heat transfer coefficient in general is not constant along the flow direction. You know why? Because for the boundary layer, you have transition zones. So at each location X, you don't have the same profile of velocity. Okay? So if you go back to the previous slide, if I consider this is my boundary layer here, okay? If I consider, for example, heat exchange at this level, the length here is different than the length here, okay? So heat exchange is varying from one location to the other, and therefore the convective coefficient is also varying from one location to the other. And this is also predicted in experiments, okay? Now, in case you want to have an average value of convection, you can calculate it, okay? So, like any averaging technique, if you know H at local level, at each location you know what is H, and you want to find the mean value of H, you can do the weighted average formula, which consists on doing integral H local at each area DAS over the total area AS. Okay? So this is an averaging technique to find the average value of H. So the average or mean convection heat transfer coefficient for a surface in such cases is determined by properly averaging the local convection heat transfer over the entire surface area. Now, in this course, I will directly give you the relation for H, okay? So you will not have to integrate, you will not have to do complex issues. Just you should understand the concept, how we get the average convection heat transfer coefficient, okay? Any question until here? Okay. Now, in this problem here, in this small problem, we will see how we can induce empirical relations into the calculation of H. Okay? So, in fluid mechanics, it is of common practice to non-dimensionalize the governing equations and combine variables which group together into dimensionless numbers in order to reduce the number of total variables. Let me explain in other terms what they mean. We said that H is determined by experiments to get empirical relations that can be used, okay? But to make experiment general, so to use the result of the experiment in a general case, you should come up with what we call dimensionless number. What we mean by dimensionless number, it's a number that involves several variables, and then when you put these variables together, you will obtain a number without units. Okay? Why we do this? Because in general, I cannot do an experiment for each case I want. I want to come up with a rule that if I have my dimensionless numbers the same in two experiments, okay, then I can say that the same result, I can get the same empirical relation from both experiments. So what I mean by this, for example, let's say this is called the Nusselt number. The Nusselt number is a dimensionless number involving the heat transfer coefficient H, the characteristic lengths of your geometry. So for example, if you have a tube, the characteristic length can be the diameter of the tube, okay? And let's say K is the conductivity coefficient of your flow. Now, if you take two cases, in order to use the same formulas, you should have at least the same dimensionless number. So they should share the same Nusselt. If they have the same Nusselt number, then you can say that I can extrapolate the result of this experiment to the other real case. Okay? So whenever you do an experiment, when you express your empirical relation in terms of dimensionless terms, so your empirical relation will involve relation between, let's say, Nusselt and Reynolds number that we will define later, okay? So when you find an empirical relation between these numbers, then your result can be extrapolated to any other case. This is the importance of dimensionless numbers, okay? Now, how we come up with dimensionless numbers? Always dimensionless number has physical meaning, okay? So let's go first with the Nusselt number. In this problem, you have a fluid and you are imposing a temperature at the upper side equal to T2 and a temperature at the lower side equal to T1, okay? So in this case, and your fluid is moving, in this case, you will have heat transfer due to conduction in your fluid first. In addition, you will have heat transfer due to motion of your fluid, so you also have heat transfer by convection. Now, the Nusselt number represents the ratio of the convective over the conductive fluxes. So if you want, the Nusselt number is an indication about how much the convection is dominant over conduction. If you have very high Nusselt number, this means that the convection effect is much higher than the conduction effect. And if you have very small Nusselt numbers, this means that conduction flux is much smaller than, convection flux is much smaller than conductive flux. So Nusselt number can give you an idea which type of heat transfer is dominant, okay? Let us calculate it together. Nusselt is defined as the ratio of the convective over conduction rate, okay? To start with, the convection rate per unit area is defined as H times delta T, while the conductive coefficient is calculated as K delta T over F. So as you can see here, I can simplify delta T from the two sides, and I come up with this term. This is called Nusselt number, and it's equal to H times L over K. And as predicted, okay, higher is the convection, higher will be H, and higher will be Nusselt, okay? And on the other hand, higher the conduction, lower will be Nusselt number, okay? So the Nusselt number represents the enhancement of heat transfer through a fluid layer as a result of convection relative to conduction across the same fluid layer. And the largest is the Nusselt number, the more effective is the convection, okay? So for example, if I give you in a problem the Nusselt number, from this relation, you can calculate your convective coefficient, because knowing Nusselt will allow you to calculate H, since from this relation, you can write that H is equal to Nusselt times K over the characteristic length, okay? And we will do problems to understand more how to do these calculations. So, if we look here at this expression, we said that heat flux per unit area of convection is H times delta T. But H can be replaced from the previous relation by Nusselt number times K over F, okay? Whereas we said K is the conductivity coefficient, Ts is the surface temperature, T infinity is the temperature of the fluid very far from the surface, and LC is the characteristic length of the geometry you are considering. So for example, if you are considering fluid flow in a tube, inside a tube, the characteristic length will be the diameter of the tube, okay? Now, as we have seen, the Nusselt number is defined as a relation between H, L, and K, okay? It's H times L over K. Now, in experiments, what we will do is we will relate Nusselt number, which is a dimensionless number, to other non-dimensional number, okay, which are Prandtl number and Reynolds number, okay? And I will explain why we are relating these numbers, okay? We have seen together previously that convection is affected by several parameters, as the fluid properties like viscosity, density, conductivity, and also by the fluid velocity and the geometry of your system. So if you want to include all of these parameters in one experiment, okay, you can define several dimensionless number and relate them. So you will look at the dimensionless number that involve the characteristics you want. So we talked about viscosity, density, and conductivity. All of these properties can be found in what we call the Prandtl number. The Prandtl number is a dimensionless number which is function of the viscosity of the fluid, the density of the fluid, and the conductivity of the fluid. So because you are interested in all characteristics of your fluid, it will be of interest to include in your experiment the Prandtl number, okay? In addition, because the velocity of your flow has a high importance in the convective coefficient, then also you should include what we call the Reynolds number. The Reynolds number is equal to rho of the fluid times the velocity of the fluid times the characteristic length of geometry. So here, as you can see, Reynolds not only includes the velocity effect, but also the geometry. So in Reynolds number, you introduce the effect of velocity and the effect of the geometry of your tube. So Reynolds is rho UL over mu. So as can be seen here, these two numbers include all characteristics you are interested in. This is why when you perform experiments, you will try to relate the following three numbers: Nusselt, Reynolds, and Prandtl. When you do this in your experiment, you can come up with a relation that is general and that can be used if you have same conditions of flows. What I mean by condition? If I have turbulent flow, let's say, okay, I can, over a flat surface, I can use this. So here, the numerical value of the Nusselt number for a given Prandtl and Reynolds is obtained from empirical correlation. As an example, if when we performed experiment for fully developed turbulent flow, so first it's turbulent, okay, and it's a flow over a smooth pipe. So here the geometry should be the same. So if you do experiment on tubes, you cannot extend the result for flow over flat surface, okay? And if you do experiments on turbulent flows, you cannot extend the results on laminar flows. So at least you should be in the same conditions. So turbulent flow, let's say, flow moving in a smooth pipe. If you have these conditions satisfied, then you can use this empirical relation for any case you have, okay? The only condition is to satisfy the same if you want a large condition of your experiment. So when you do experiments for fully developed turbulent flow, you cannot use results for laminar flow. And when you do experiment on tubes, you cannot extend it for flow over a surface, okay? And this relation developed experimentally can be used in any problem satisfying the previous conditions. So now, next time, hopefully, we will solve together problems on this, okay? So please, for next time, I also prepared for you a list of YouTube links, but 2 of these YouTube links involve problems. So if you go to it, I will post it, if not today, tomorrow I will post it, okay? They are marked in red. The red links involve problems. So you have a lot of problems. I did this to help you to practice, okay? And if you are not of a mechanical or chemical background, it can help you in knowing more the equations that we use, okay? So you will have a lot of details on how we calculate conduction, convection, radiation in these examples. So please try to go over the YouTube links I am giving you. Try to practice. And if you have any question, you can ask me directly on WhatsApp, or you can ask me during the session, okay? And next time, we will continue the slides and we will start doing problems together so that you understand more the concepts. Any question?
No, thank you.
Okay. So see you hopefully next time. Bye bye.
Thank you.
See you next week.
Yes.